Good afternoon. Welcome to today's webinar. My name is Tracy Noble with ABB Power Systems, and I will be moderating today's webinar. Before we get started, I wanted to go over a few housekeeping items. All participant audio will be muted during the event. If you would like to ask a question, please use the question box on the GoToWebinar panel. We will answer as many questions as possible at the end of the event. Please ask your question during the presentation so it will be available. Today's webinar is being recorded. A link to the recording will be emailed to you following the event. Feel free to forward the link to people you know would benefit from the presentation. A little disclaimer from our legal department here at ABB. ABB is pleased to provide you with technical information regarding protective relays. The material included is not intended to be a complete presentation of all potential problems and solutions related to this topic. The content is generic and may not be applicable for circumstances or equipment at any specific facility. By participating in ABB's web-based protective relay school, you agree that ABB is providing this information to you on an informational basis only and makes no warranties, representations, or guarantees as to the efficacy or commercial utility of the information for any specific application or purpose, and ABB is not responsible for any action taken in reliance on the information contained herein. ABB consultants and service representatives are available to study specific operations and make recommendations on improving safety, efficiency, profitability. Contact an ABB sales representative for further information. And now on to the fun part, line current differential protection with Roger Heading. Roger graduated from Marquette University and joined Westinghouse Electric Corporation. After receiving a master's degree in electrical engineering from the University of Pittsburgh, Roger became a district engineer and eventually moved to Milwaukee, where he currently resides. As a relay development consultant, he guides the development of relay products for the North American market. Roger is an IEEE senior member and vice chair of the IEEE Power Systems Relay Committee. Roger has authored or co-authored many papers in power systems protection. And I will now turn it over to our speaker, Roger Heading.
Thanks, Tracy. And thanks all for joining our seminar today. Hopefully, you'll all take away some things from this seminar. First is, what is a line current differential relay? What is a current differential relay? And what are the application issues of line current differential relays versus line distance relays? These are the two major relays that we use in protection of our line protection of power systems, so it's good to know different issues regarding each of the two types of relays. If you have any questions along the way, please put them in the chat box, and either myself or Elmo will be able to answer those for you. So what we'll be doing in this seminar, we'll first give an introduction to a line differential relays and differential relays in general, and then talk about what's specifically different about a line current differential relay than a differential relay. Next, we'll talk about some application issues regarding the line current differential relay and different ways they can be applied. And, of course, it would not be a complete discussion of current differential relays unless we talked a little bit about communications issues and communications, because it's a major part of the relay. And then we'll talk about a summary of some of the things that you've learned over the period of the next hour or so. Starting off with what a line differential protection application is. Here we see a single line diagram of a transmission line with breakers at either end between buses A and buses B, and we see oops, backwards. We see CTs located at each end of the line on the bus end of the breakers, and feeding into an 87 type relay. The 87 type relay is a differential element, and the information is exchanged over communications line between the two 87 relays that share the information, and then each terminal makes a decision about whether to trip or not, depending on whether the fault is internal or external. It's all based on the simple Kirchhoff's law that the current entering node has to be equal to leaving the node. So some things we can take away from this is the line current differential relay is unit protection. That means the protection is only concerned with what's between the two current transformers, what's between the two sets of CTs. Anything external to the CTs is not any protection zone. So we have a definite area of protection that we're limiting our protection. The test simply is then to determine if the fault is within a protected zone or outside the protected zone. In this case, protected zone for differential relays could be the transmission line terminals, it could be power transformer terminals, or bus terminals. The same principle applies to all three. So we measure the currents at all the terminals of the protected circuit, and then we transmit information about these currents to the remote ends of the line. Each of the remote ends of the line then compares all the currents together using classical current differential principles, and then supplements this some logic for CT saturation or open circuit CTs, and then decides whether or not the fault is internal to the area of protection or external to the area of protection. Of course, the system has to be highly dependable, have a high dependability, which means it must operate for all faults within that protected zone. At the same time, it has to be secure, so it does not operate for any faults that are outside the protective zone. And also, by the nature of the beast, these should have good performance during evolving faults or cross-country faults involving separate phases on parallel lines. Because it's a current-only scheme, we're immune to power swings, mutual coupling, or that series of impedance unbalances that we have to worry about in the normal. Just as we would have it now that my telephone stopped working and call failed, so we're switching over to using a speaker system on the speakers off of our computer for the presentation now. The measured line, so as we were saying before, because we're sending sample data across the line, it's very easy to calculate the sequence components and harmonic components, which makes application of these relays to certain areas where they weren't applied before much easier, as we'll see in a little while. As we said, line current differential basics is we take currents from each end of the line and sample that information and send it to the remote end of the line. So each end of the line has local information and remote information, and it does a comparison at each end. Because we're only using current transformers, we're not using any voltage transformers. Therefore, we don't have any worry about fuse failures in CCVTs or CCVT transients or power swings at all. We can make the relay very sensitive to detecting ground faults, much more secure than distance relays. It's very easy to do segregated phase, shooting each phase separately. So it's ideal for revolving faults or cross-country faults, for single fault tripping applications, or series compensated lines. And the communications dependent type of system. That's the only ground fault would be a communication dependent system. Okay. The current, so we have current relay. The earliest types of current differential relay were first analog type current differential relays, and then digital type of current differential relays. After that, another type of current only scheme would be a phase comparison relay. Phase comparison used to be segregated phase comparison, combined sequence, or the direct. The phase comparison isn't used much longer, and most current only schemes now are current differential type schemes. A current differential relay in itself just looks at this protected equipment can either be a transformer, a line, a bus, or whatever, and we take a current on each side of the piece of protected equipment, hook the current transformer up so that polarity is away from the piece of equipment, so that the current are both in towards the relay, and we virtually measure the current going into the protected equipment and out of the protected equipment. And if we have a through load current or a through fault, the current is running into the device and out to the device, and so IL and IR are equal to each other. And if there's an internal fault, then IL is not equal to IR, and the current all goes through the relay coil, and the relay operates. So basically, for an external fault, IL is equal to minus IR, so that the sum of the two IL plus IR, the local plus the remote, is equal to 0, and the relay doesn't trip at all. Here we see the currents at the local end of the line and the currents at the remote end of the line. For an internal fault, the summation of the local current plus the remote current is not equal to 0, so therefore the relay should trip. So here we see the pictorial view of the local end of the line and the remote end of the line, seeing the currents look to be in phase with each other, so the actual current through the relay is 2IL for this case. This is a simple case where, and if you looked at the operating characteristic on a polar plot, you'd see that if we divided IL, the local by the remote current, we would get a restraint point of -1, where the relay, where the IL and IR are equal to each other, and anything around that point would be an operate point. But we know in real practice that always IL and IR aren't quite equal to each other because of other factors, so that in order to make the relay much more secure for external faults and sensitive for internal faults, we wound up putting a restraint quantity in the circuit, so that we not only have an operate quantity, but we also have a restraint quantity. So now that we not only have to have a operate current, but we also have to have an operate current above a certain restraint current level in order for the relay to operate properly. Oh yeah. I'm sorry, but there's some conversations taking place in the background of where I'm giving this presentation, so that's what you wind up hearing. I can try dialing in again, rather than going we'll make it a little bit clearer as we go on. Let me try dialing in while we're talking. And then we'll make it a little bit clearer. Excuse me for a moment while I put this access code in. Yeah, I tried to download something to telephone now. Hopefully you can all hear me now. Tracy or Elmo, if you would just send a chat message that says that this is better, that would be fine. Okay, so now we know that I hear. Okay, great. Let's continue on then. So now we have a restraint winding and also an operate winding. Now we can write equations for the operate current versus restraint current. We always want the operate quantity, which is in most all cases IL plus IR, to be greater than our restraint current. Our restraint current can be given in several different ways, and they have been used in several different methods of describing the restraint current on different relay systems for various current different relays. One possible method is having K times the absolute value of IL plus the absolute value of IR is one method for describing the restraint current versus the operating current. Another way of describing the restraint current is some factor K times the value of IL, absolute value of IL minus IR. And another way of describing the operating current is just some magnitude K times an Imax value. All of these two have been used for different methods of describing the relationship between the operating current and the restraint current. You may recognize the K times the absolute value of IL minus IR was what was used in the LGB2 relay some years ago. Some competitors have used K times IL minus IR, and our latest generation of relays uses this value of K times Imax, where Imax is the maximum current, phase current, in any one of the phases at any one of the terminals. Because now we have a relationship between the restraint current and the operating current, we also have an operating curve for the relay. So we have actually three different slopes for the modern microprocessor relays. One is a straight line 0% slope that's good up to a certain point of like 1 per unit restraint current. The next has a slope of about 40%, which you see in the red area, and this is good between 1 times and 3 times the normal restraint current. And then above that 3 per unit restraint current, we have a line that goes up at an 80% slope, and that 80%, yes, a question comes in from the audience, one of you, is that is K settable? On most of the older relays, there was a fixed value, like on the LGB2 relay, K was set to 0.707. And on some modern relays, K turns out to be settable relay. And then in some relays, the K is actually set at 1 instead. So it can be settable in some relays, and in other relays it isn't. So now that we have this relationship, we know that any current that is below this operating curve will be the relay will restrain from operating, and any current that is above, any time that the operating current is above this restraint current, you will be in the operate region. Why do we have three different slopes for this operating curve? It's based on the fact that all current transformers are not going to operate exactly the same. And the more current you put through the current transformer, the most probably you'll get some error current out of it. So in the first region and very low current values, we feel that the current transformer would be performing very well. That's why we have to have minimum IED current that it really operates for. That's like a half per unit per unit. Then when we get between 1 per unit and 3 per unit of current, we feel that you're going to get some error current out of the current transformer, and that error current will not. So we increase the we increase the operate current for this given amount of restraint current, so that it compensates for this error current from the current transformer. Then when we get about 3 per unit or so upwards, much higher current level, we're pretty sure we're going to get some kind of CT saturation or so. Now we have to have much more operate current for a given amount of restraint current before the relay operates. That's hence the 3 different parts of the curve that you see. On most relays, these points of the curve, the minimum operate point, the break point between the 0 slope and the 1 slope, and the break point between the 2nd slope and the 3rd slope, these are all settable values, and also the percent of the slopes is also settable. But for 95% of the applications that you would have for current differential relays, you can set the one that leave it at the default value of 40% and 80% for the 2 different slopes. Now, if we take that analogy of that what we did for a current differential relay, and we expand it to a current differential relay. In our previous relay, we had one relay that was protecting a piece of equipment. In our line of current differential relay, now we have 2 terminals physically separated by some distance, anywhere from a half a kilometer upwards of 200 kilometers apart from each other. So therefore, we have to have 2 relays, one relay at each end of the line, and some communication equipment between the one terminal and the other terminal, between the 2 terminals, in order to make this comparison, or this differential circuit. So we can see the same sort of a circuit, though. We have a protected line. We have the current transformers at either end of the protected line. We have a relay at each end of the protected line, and we have this communications path between the 2 relays that we need to worry about. And we still do the same comparison of the local with the remote signals at each end of the line. We develop a operate current and differential current based on the relationship between the restraint, the local and remote terminal currents. Here shows a couple of examples of this happens to be for an external fault where you see the currents are actually out of phase with respect to each other for each of the phases, and for an external fault. And for an internal fault, you'll see that it's mainly fed from one contribution from one end, but you can see the currents are more in phase with each other for an internal fault, as you would see on the previous slide. So we have so this is another picture of that same diagram we saw before, where we have a setting for the relay being ID min, which is the minimum differential current operate value that we have for the relay. And that's because this can be set anywhere from 0.2 upwards of 0.5 per unit of the base current of the relay. The base current is normally the size of a current transformer. So if you had a 1205 current transformer, then the setting would be in the area of anywhere from 200 amps to 600 amps for the setting for this minimum operate current. And then we have an N section 1 and N section 2, which is, as we said before, anywhere like that you can leave fixed at 1 per unit and 3 per unit. And then we have the slope of section 2 and slope of section 3. And I said before that this normal slope of section 2 would be set at 40%. The slope of section 3 would be set at 80%. In addition to this normal operating slope, this would be the conditional operating for the relay. We also have what's called the unrestrained limit. This limit on modern relays, this dates back to even in the less protected relay. We would have an element that no matter how high the restraint current was, if the operate current got up to this level, it would operate, period, regardless of what the level of restraint current is. So that's what this unrestrained limit is. ID min high is a value that's used on some relays, and this is used if we have a open circuit CT problem, so that we actually shift the level of the operating of the relay to compensate for that open circuit CT, rather than shutting the relay down. And we'll go on further. So the first generation of current differential relays had very, very reduced communication requirements. Matter of fact, the communication between the two ends of a line was simply a twisted pair of number 14 or number 16 or number 18 wire between two ends of a line. So thus that the separation between the length of line that this would protect would be somewhere less than 2 miles long for the maximum line length for this first generation of current differential relays. And it used a sequence filter. A sequence filter that you might be familiar with a relay like the HCV pilot wire relay, which was the first current differential relay that was made by Westinghouse back in the turn of the century. Here we had a protected line as we had before, as in modern days. We have current transformers at current transformers at both ends of a line. But now the current transformers would feed into a sequence filter, and a sequence filter, if you remember, would make the relay responsive to positive, negative, and zero sequence current, and it can actually had taps on the relay for matching to positive, negative, and zero sequence current. And the output of the sequence filter was a sequence voltage. And the sequence voltage was then impressed on the pilot wire. And then at the road end of the line, it used the same sort of sequence filter, but so the currents would run through the sequence filter, and again, it would develop a sequence voltage, VH, that was impressed on the line. So when we had a through fault current, we would get a circulation of current. The polarity of VH and the polarity of VG would be opposite each other, so we get a circulation of current on the transmission through the pilot wire, and no current through the operating coil at all. When we had a internal fault, then the respective polarity of VH to VG would reverse with respect to each other, and so that we would get no circulating current, but all current would go through the operating winding, and the relay would operate. It's a very, very simple relay. Actually, the relay was made for a long time, and it's still being applied in several locations. The problem with this approach, though, was that the relay could only be used with this pilot wire, which is twisted pair. And the most of the problems with the relay were dealing with this twisted pair, where the twisted pair would become shorted or open-circuited, or it would be out of the utilities control, and it would be controlled by the local telephone company, and they would stop even supplying the twisted pairs, and they would just supply fibers instead. But no matter what and if to be too far apart from each other, you can have station ground map potential rises between one station and the other one, which would induce a current on the pilot wire. So there's several things that were going against the use of this type of scheme, but two of those being the rise in station ground potential and induction of current into the twisted pair from the power line circuits. But over the years, there's been several different remedies that have come to play, using twisted wire pair, using the gaps and arresters across, so we limit the amount of potential rise on either end of the twisted pair, using drainage reactors, neutralizing reactors, and insulating transformers. Using this compendium of devices, we're able to get a pretty decent pilot wire HCV relay system. But again, you were limited by the length of the length of the wire that you can use. And because of the amount of capacitance in the twisted pair, you were limited to a certain number of microfarads worth of, and also the total loop resistance for the HCV had to be less than a certain amount. So that kind of limited how long you could even have for that HCV. So it's limited to less than 2 miles. So historically, when the new generation of current differential relays came out, people had in their mindset that same idea that we have to limit the use of current differential relays to less than 2 miles long. But in actuality, with the new types of communications equipment we have, you can run current differential relays upwards of 200 kilometers without any problem at all. When we go from using a metallic type twisted pair to a non-metallic type communications being fiber or something, then a couple other things that we didn't have to worry about before. Now we need to worry about propagation delay time. Propagation delay across the transmission line. We have to worry about time synchronization, so the samples at both ends of the line we're comparing apples to apples. We need to worry about signal corruption across the line. And we have to worry about communication networks, which means you have to worry about bits and baud and bandwidth and switching and multiplexing and all that other kind of stuff. But we also are able to incorporate backup protection into our current differential scheme. So that if we do lose communications for some reason, we can rely on some backup protection, whether it be a simple overcurrent relay or whether it be a distance relay that we use for backup to back up the current differential if we should lose the communications channel. So there are remedies to this. I see a question Elmo came up with. Was entering and missed the context. PU normally means per unit. Pickup is pickup. PU is pickup. So I'm not sure what he's referring to there. Maybe it's way back over here. No, I don't know. Well, we'll come back to that later, Elmo. Where were we at now? Okay. Now we go back to, so the first generation of numerical relays, which were used, transmitted Fourier coefficients across the channel. What they would do is they would do a Fourier transform and develop the Fourier coefficients, like A cosine theta plus J sine theta representation for that line, and transmit those coefficients over the line, and use that to determine that information. Very well, just using that limited information across the channel because the channel was limited to what could be transmitted. In the newest generation of relays, though, instead of setting just Fourier coefficients across the line, we now can send sample data across the line instead. So by sending sample data across the line, we not only know the 60 Hz quantities, but we can do a total harmonic analysis and know such things as the second harmonic and fifth harmonic and all harmonics of that signal, and can also calculate sequence components based on that information. You'll see how we can use that information in a little bit now. Segregated phase protection calls for a large information exchange. Segregated phase protection means I'm keeping each one of the phases separate and transmitting that phase information for each phase separate from each other. The other method, of course, would be to use a combined sequence component, which means I do similar to what we did in HCV, and I combine all three phases together in some way and transmit one composite signal line, and then do an operation on that signal. That works very well, and it minimizes the data requirements you need, and extent of the channel could be set to be less than 4 kilohertz if you use that of a approach. But you lose some phase segregation to do that. You don't, phase identity about which phase the fault is on. But if you're doing 3-phase stripping, that's fine. On modern relays and modern communications techniques where you have 64 kilobit channels or so, it's very easy to send enough information that we can use segregated phase differential instead of combined sequence differential. So now that we have all this phase information, we can deal with cross-country faults, which are faults that are, if you imagine a parallel line, two parallel lines on the same tower, and I have a fault between A phase on one on one line and C phase in another line, I can distinguish those apart from each other. But if I'm using segregated phase information, I can deal with series compensated lines or single pole tripping, all those things very easily with segregated phase approach. As far as the fiber limitations, the fiber could range anywhere from, our line lengths could range anywhere from 1 kilometer upwards of 160 kilometers, and there are manufacturers that have different types of fibers that they can use. Our short-range fiber would be good for between 1 and 3 kilometers. A medium-range fiber would be good for between 3 and 50 kilometers. And a long-range fiber would be good for anywhere from 51 to 160 kilometers long. Each one of these would be using a different sort of an edge-emitting diode for the light source into the system. Now, I think that, whoops, back up again. Where did I go? The short-range fiber, short-range is typically a multi-mode fiber, and the medium range and long range are typically single-mode fibers that they're using. Another communications channel that is being used quite successfully is the G.703, or you could use a fiber into a multiplexer rather than using a dark fiber. All of these could use the C37.94 multiplexer standard, which is a standard for interfacing between the IED and the multiplexer. Let's now look at another portion of line terminations. We oftentimes talk about the line protection between the two terminals, but we don't much talk about the protection or about what line terminations at all, and that's what we're going to talk about here. We're going to talk about a single breaker application, a ring bus application, a breaker and a half application, and a transformer application. Yeah, with that, the question came up, can we email a PowerPoint? The PowerPoint will be available to everybody shortly after the presentation, and Tracy will send everybody a link to how to get a hold of that presentation. So if we have a single breaker, remember we have information coming into a line differential relay, and a single breaker is very easy because the current going through this one CT is the same as the line current going out of through the breaker. So we just have one connection between the CT and the line current differential relay. That's pretty straightforward. When we get into a ring bus or breaker and a hash scheme now we have to worry about, we have two different breaker CTs that are going to be fed into the relay, and how to connect these CTs into the relay is the question then, because we have the current through one breaker plus the current from the other breaker adding together to come out with what our line current is. The conventional approach was to use a single input on the IED and connect these two current transformers in parallel and bring them into the relay. As you see right here, we're connecting both relays external to the relay in parallel and bringing them into one relay input. What this does is that we lose a lot of current transformer information. We don't know if either one of those two current transformers is short-circuited, if either one of those two current transformers is open-circuited, or there may be saturation occurring in one of the current transformers, nor do we know any information about the metering information. Another question came in, I am slow. The C37.94 standard permits greater than 160 kilometers length fiber. Actually, the C37.94 doesn't really say anything about line lengths at all. The limitations on the length of line that you can have with a fiber It's dependent upon the losses on the fiber and the amount of the receiver sensitivity and transformer capability of the current differential relay scheme itself. They don't really deal at all with C37.94. What I gave an example previously was just talking about the limitations that we normally define for different lengths of line, not what C37.94 defines these lengths of line to be. Not here again. Okay, so now, and we not only lose metering information, but we also lose the larger restraint current. Because we're adding two currents together, coming into one input to the relay, we have a much larger restraint current than we would have had if we kept these two currents separately. Therefore, we reduce the sensitivity of the relay. Here's an example we're talking about. If I had the two CTs added together, and I had 2 per unit current coming from each one of the CTs, then my restraint current would be here at 4 per unit, and my operate current would be, because I would be way out here on the curve, would be up around 2.8 or 2.7 per unit operate current. If I kept each of the CTs separate, remember I'm using the largest of the currents in each one of the phases for my restraint current. If I keep the CTs separate, then I only have 2 per unit current as my restraint current, and my operate current based on a 2 per unit restraint current is only going to be about slightly over or slightly less than 1 per unit current. So I'm gaining much sensitivity by keeping these two current transformers separate. So our preferred way of doing this is to hook the two CTs and coming into separate inputs into the relay. And so we now have all the information about each of the breakers, all the information about the CTs. If one CT happens to be putting out no current because it's saturated or because it's open circuited, we know that at the relay now. And now we can, if we want to have a breaker feeder relay built into the non-differential relay, and because currents are separate, we know exactly what the currents are through that one particular breaker if the breaker happens to fail and not to open properly. Let's look at another one of our fine examples, and that's a transformer terminated line. Here we have a transmission line. The only difference is that instead of having a high side breaker on the line is terminated in a transformer with a low side breaker instead before we get to the relay. So the relay CTs are on the low side of the transformer, and on the remote end of the line, of course, on the between the breaker and the bus. Because we have a transformer terminated line, there's certain things we need to worry about, as we did with our transformer differential scheme. That is, when we energize this line and we close the breaker at the far end of the line to energize the bus and the line, we now need to worry about a transformer inrush current flowing into the transformer, which doesn't appear on our low side breaker at all, but appears on our high side breaker. We also need to worry about low side faults out here too, how to protect for those. So those are a couple things we're going to talk about right now. So the things we need to worry about is inrush current that's flowing on one side of the transformer, and so it goes through one CT and not the other CT. We also need to worry about, because if this happens to be a delta wide transformer or a Y delta transformer, then the current at the one side of one CT is not in phase with the current on the other CT under normal conditions, and we need to account for that phase shift across the transformer. And if we have low side faults on the secondary of the transformer, and using this CT may, because it's a delta Y transformer, the CT on the low side may see this fault, but the transformer on the other side doesn't see the fault because of the problem with the delta Y transformer and the current being trapped in the delta. So these are the things that we worry about in transformer protection, And we also would have to worry about that in using a transformer terminated line in having a transformer in our line section. But remember, back when we talked about communications and transmitting information across the line, we also mentioned that you can transmit sample data across the line. And because we're transmitting sample data across the line, we can calculate what, at each terminal, what the harmonic components are. And just as we do in transformer differential protection, we can put a harmonic restraint element in the line differential relay and set it so that it can detect this inrush current and block the relay from operating during this inrush current condition. So that's fairly easy. Also, with our numerical technology, we can for a delta-wide transformer, we can physically shift or internally to the relay. We can just tell the relay that we have a delta-wide transformer here, and it will shift the currents on the secondary so that numerically the currents are in phase on both sides of the transformer, so we can do the differential calculation without any errors. So the last thing I need to worry about would be a low side faults on the transformer. I just talked about that. So we'd use a second harmonic restraint element if ever we have a fundamental current above 60 hertz current above 7% of the fundamental, then we would block the relay from operating. So now let's look at the next example. Is if we have an external fault on the low side fault on the transformer. So now we have current, that's opposite of our inrush problem, and now we have current flowing on the low side of the transformer through the CT and to the ground fault coming up through the grounded Y winding of the transformer, where we don't see that on the delta side at all. When this occurs, of course, this would normally, as we know from transfer protection, this would cause a misoperation of our transformer differential, and in this case, line current differential relay. But just as we did in our modern microprocessor transfer differential relays, we can put in a zero sequence trap on this Y winding and this Y termination here, so that we block any zero sequence current flowing. Or we not block, but we just discard any zero sequence current flowing through this CT, so that we don't operate for a external ground fault. Another example, so we use zero sequence elimination, and we used to do this with, of course, a zero sequence trap with an auxiliary CT, but now we can do that same thing in the relay now. Another example would be a tapped line, and where we have a transformer, we'd have a tap line with a transformer connection on the at the tap. We used to handle this by just setting the value of the pickup level of the 87L element for this example above the value of the load current on this tap. That we don't need to do that anymore, and we can handle this another way. Here's an example of a secondary fault that we would have on the tap, where even if we set this above load, even if we set this above load current, we could still possibly get a misoperation because of this secondary fault. But we know a couple of things about a fault on a secondary of this transformer. Number one, we know that there's a transformer impedance associated with this fault. So that fault current at the tap is going to be much less than a fault current flowing on the line and a fault current flowing down to the tap. So we know, so we could use that information in our relays. We use that information in our relays and devise a method to distinguish between a high side fault and a low side fault. Because we know that a line fault will be a 1 magnitude of current, and our transformer secondary fault will be a much smaller magnitude of current. And we can use a level detector that detects any current above this will be considered a line fault, any current, and we would operate instantaneously. And any current below this would be a transformer secondary fault, and we can time delay the operation of our line current differential relay to let the overcurrent relay that's on the secondary of the transformer operate first. So that's kind of shown here. So in that particular case, we have full instantaneous coverage on for the entire line section of the line, plus down to the transformer tap to the transformer, and then anything below this, any faults below this level will cause a time delay operation of the relay. So it coordinates with this low side breaker down here in the relay at the low side breaker. So that looks kind of like this, where we have we can actually choose a ID min, and we can choose a curve that we can coordinate with, so that we actually coordinate the delayed clearing of any fault down here to let the overcurrent element that's on the tap operate first before we operate. So we have instantaneous clearing in this particular area, and then time delay clearing in this area down here, based on the curve that we choose. And then we add some delay time to it. So that's how that's done. Another question came in earlier that I didn't look. I'm sorry. That said, how about using a T1 or RS449 communications line? A T1 line could be used easily with these protections. That's what the multiplexer would be. You would feed the short line, the short multimode fiber length is less than one kilometer length into a T1 multiplexer, and then you should T1 line for that. That's what that short line is used for. Hope that answers that. Okay. Next, if we have a next area of concern is a high resistance fault. We don't want to operate we want to be able to clear a high resistance fault, and the way we do that is using a negative sequence element. We know that a negative sequence it could be shown to operate as so it emanates from the point of the fault. So here we can see a negative sequence generator at the point of the fault that's pushing negative sequence current away from the fault. Then using our negative sequence differential element at each end of the line, we can then determine whether or not there's a fault on the line. Because if it was a external fault, a fault located even on the terminals, then our negative sequence current would be a through current. Or by our CTs, they would be 180 degrees apart from each other by the way we connect the CTs. But if the fault current was internal, then the currents would be going away from each other. But by our CT manipulation, they're added together. So we get a operating curve that looks like anything to the left of the right of this horizontal line would be a internal fault. Anything to the right or left of this would be an external fault. But to give it a little bit of a hedge, we actually set a relay operate angle that's somewhere around 60 degrees or so that we cover 120 degrees here as an internal fault, and then over here would be an external fault. So this is by doing this, we can set this negative sequence element to be very, very sensitive, much more sensitive than our normal ID minimum operate level. For the ID minimum operate level may be 0.3 per unit current. This negative sequence element could be set for 0.04 per unit, so much more accurate, 10 times more sensitive than the other element. Another question came in: can you please also discuss transformer inrush with auto transformer banks? I'm not sure what the question means. What we talked about before was regarding transformer inrush back here. I'm not sure what the question is. So we have whether or not if you have a YY transformer here, then we don't have the problem of having for our external fault problem. We don't have a problem of distinguishing this. We don't need to use a zero sequence trap because the current will be essentially Y-Y transform will be going all the way through the transformer. But as far as Inrush is concerned, I'm not sure what the question is. Whether you have an auto transformer or a delta Y transformer, you will still only be energizing one part of the line compared to the other part. We usually energize that from just one of the windings. So I'm not sure. Maybe we'll go back to that question a little bit later. Okay, now that we covered that, our resistance fault, now the next thing we need to worry about is capacitive current compensation. And what that means is that if we have a transmission line, we're going to have a certain amount of capacitance on the transmission line. And the capacitance on the transmission line looks like the charge current on the transmission line looks like it's a through fault or an internal fault because it's current that's going into the line and not being seen at the remote terminal. What modern relays do now is that they could, under steady state conditions, means I energize the line and the breaker's closed for a period of 500 milliseconds. We can measure that line charging current and take that line charging current and subtract it from our differential current. So our new level of differential current doesn't have the charging current component anymore, which means we don't have to allow for the line charger current when we set our minimum differential operating characteristic for the minimum operating point for the line. So we're already compensating for this charging current. So what we do is we measure the fundamental frequency of the differential current under normal steady state conditions. That means 500 milliseconds after the breaker is closed. And we have no start signals or external fault type indication. Then we subtract out that charger curve from the differential current to zero it out, so we don't need to change the minimum operating level at all. So now let's talk a little bit about communication. So there's various types of communications that you can use with this line, and so this is a typical example of a three-terminal line where we have this IED 670 happens to be, I'm sorry to put down there, that happens to be a name of our line current differential relay. So we have three terminals of line current differential relays, and we have the communications between each of these. Each terminal is communicating to the other two terminals in a normal three-terminal line that you see here. And they all share the information together. They all make their decisions independent of each other. You can have up to, with modern microprocessor relays, up to five terminal line. So we can have 3 taps on the line plus the normal line end, and this would be, so I'm not saying your planner should plan for a 5-terminal line. That would be something I wouldn't want to deal with either, but there are, you can get multiple communications modules in each one of these relays to support something like a 5-terminal line. A more practical application of these multiple communications modules is something like this, where we have a breaker and a half scheme at each of our terminals, and now we have 2 current transformers that we want to bring information for into the system at each terminal. And because of the 5 communication modules, we have 4 communication modules we have available on each relay. We could supply all the remote CT information to each of the relays to have a great communication system. And in this type of a system, we will also be able to provide information about each of the CTs and its information to each of the remote terminals. When you do this, I could be sitting at one terminal, and I could actually see all the currents flowing on each of the other lines and each of the other CTs coming into the system. So it's very powerful to have all that information available at any one terminal without having to ride through the line. when you talk about communications, and you can't get around talking about route switching and delay symmetry and that kind of stuff. When most times you don't have dark fibers to use, and you have to use go into a multiplexer, like one gentleman said, going through a T1 multiplexer or higher level multiplexer to get the information from one terminal to the other. So if I want to go from terminal A to terminal B, and my normal route would be from A to B, but in some cases I may get a break in the terminal, like you see here, this break between terminals A and this midpoint. And if that's done, then I get my system gets rerouted over this longer path back to B again. And that be the case, or we may get a channel asymmetry. It may go from A to B over the red in one direction, but then when it goes from B back to A again, it follows another path across this green path instead. In either case, we don't have a channel symmetry between the path going from A to B and B to A. The conventional method of lining up the signals between the two relays is to use a echo type of signal, which means that doesn't show that on this picture. Sorry, it's echo type of signal, which means I start a timer when I send a signal from A to B, and then B takes that same signal and sends it back to A again, and I take the transit time from A to B and from B to A, add those two times together and divide by 2, and that's my channel delay time, and that's the channel delay time I input into the relay, and that's how I line up the two signals together. And that works just as long as the path from A to terminal A to B and B to A is the same. But as soon as I start switching and I start getting a path from A to B that's not symmetrical, and it follows some other path from the other way instead, now you can see that the time it takes to get from A to B and the time it takes to get from B back to A again is not the same. So that if I set my relay based on the time it takes from A to B and B to A divided by 2, I would have the wrong information. So there's limitations on how much of a channel delay you can tolerate. Dissymmetry you can allow before the relay doesn't work properly. So that modern relays, what they're done now is instead of using a echo timing, they put a GPS time synchronized signal at each terminal. Using a GPS clock at each terminal, now each of these signals, each of the samples is time tagged by the GPS clock, so that when it gets to the road end, it doesn't care how long it takes to get there. It's time tagged so that when it gets to the road end, it knows exactly how to line it up with the remote end. So it's very easy. So it's recommended that anybody. Yeah, the question comes up: does your relay communicate directly to RS-422 as well? It can through a multiplexer, yes. But our normal way of doing things is through a direct fiber into using a. See that 422 is a electrical interface rather than an optical interface. So we have ways to do that, yes. But go back to our generic thing again. So we have a GPS synchronized signal at each terminal, so that it doesn't matter if it takes whatever route it takes to get from one point to the other one, bouncing back and forth, is immaterial as long as we time tag that sample, so that we line up the time tag samples together and do the comparison at that point, the current differential algorithm. So that's the recommended way of using the relays nowadays is through a GPS time synchronization. Sometimes you might consider using a redundant network where you want to for sure have a good telecommunications path between one terminal and the other terminal, and you may worry about the telecommunications channel not going down for some reason. If that be the case, there's options available so you can have a redundant communication channel running in parallel with the preferred channel, and it doesn't take any action at all until a preferred channel goes out of service. Then the redundant channel takes over again, and it doesn't lose a beat because it's already synchronized with the rest of the system, so it takes over the protection as it is. The next is that there's two different ways that one relay can communicate with the other relays. One is called a master-master, and in master-master communications, each of the relays receives all the information from each of the other relays. So as you can see in this particular scheme, each relay is receiving all the information from each of the other relays. And each relay then makes its own decision about tripping and does its thing and then tells the other ones that it's tripped. It's called master-master communications. Another method of doing this to save communications is to do master-slave communications. In this particular way, one relay becomes the master, and it receives in-channel information and it's from current information from each of the other relays, and it decides, does the current differential calculation, and then sends a trip information back to the other relays if it decides that it needs a trip. Of course, if this relay goes bad, then this won't work. But it's a good way to save on communication channel between if you don't have enough channel to connect all the relays to each of the other terminals. The relays our relays happen to have a separate communications card that you're able to put into any of the other relays. Here's an example of a master-slave that's been done before. There's a case where we have a transformer terminated line, as we showed before. In this case, we have an RET67, which happens to be a transformer differential relay doing its normal protection around the transformer. But in this particular case, we put in a LDCM module, our communications module, in the RET670. So we're taking the information from the high side of the transformer and feeding that information to the remote end of the line, where we have an RED670 relay. The RED670 is a line current differential relay. It does the calculations about if there's a fault on the line section, on this line section, and if there's a fault, if it determines there's a fault, it sends a transfer trip back to this RET670 to trip the low side breaker. So this is an example of how you can use a master-slave example where you don't have two of the same relays on each end of the line. Here's an example of a multi-current line differential relay, just for your example of what types of things that we have in modern relays now. If you have a two-breaker scheme like you see here, we have CTs, of course, coming in separately from each of the breakers. So each breaker has its own breaker failure relay built into it. Each breaker has its own reclosing relay built into it, and sync check relay built into it. And we also have a normal 87L relay and still bus protection built into the scheme also. So these are the complement of relays that we would have for the line current differential relay. And also you see here 3 zones of distance protection that's there in case we have loose. We can either invoke it on loss of channel or have it running in parallel with the line current differential scheme. So that kind of concludes our presentation today on line current differential relays, and hopefully you've gotten some information about what current differential relays are about, what line current differential relays are about, and some issues regarding line current differential relays, which are slightly different than those issues with line distance relays. If that's all, thanks for your participation in the webinar. We'll get back to each of you with an email in a short time that you'll be able to get a copy of this webinar and the voice, so that you can review it at your leisure and share with others. So that's it. We apologize for any audio problems we had with this. I happen to be in a remote location at a hotel, and that's under construction, so we're getting some noise in the background that I don't have much control over. They try to put me in a room that's away from that stuff, but it seems I'm still getting that kind of interference. So if you have any questions, you can pose them to us, and we can answer some questions if you have any questions at this time. Were there any unanswered questions, Elmo? So if anybody does, if you have any questions, you can always send us emails about that like we have in the past. You have our email addresses, and we could take those. A question came up, can you use a twisted copper pair for communications medium instead of fiber, since the speed of a copper is approximately 0.7 times the speed of light? Explain why. The main problem with twisted pair copper is the problem you'll get by connecting two lines remotely together with a piece of copper. It's the same problem that appeared using the pilot wire type relay. You can get, if the lines get farther apart and because the solar resistivity is different, you can get some rise potential across that copper wire that would cause some problems. And there's many issues associated with using a twisted copper pair rather than using fiber optic. That's why the preferred method of use of the transmitting communications information is over a fiber instead. Another question came up, is your RED able to talk to the RED in the line differential mode? RED, yes. Yeah, the RED, actually the RED 670, in that example I showed a while back here, the RED is talking to the RET 670 and exchanging information with it. And it's actually one-way communication. The RET sends this line data to the RED 670. It does the analysis, and if it calls for a trip, it sends a trip back to the RET that trips the breaker pin. A question came up again. I mean, in the future, which protection is going to be most used as a principal protection, the differential or distance? I guess different people have different thoughts on this, but since communications are getting so easy to come by now, with one or more fiber available, and the ease of putting in line current differential relays is number of settings you have to have on a line current differential relay versus the number of settings you have to have on the line distance relay is so much less. There's always going to be a place for line current differential relays in the future, and may even surpass distance relays. And even NERC requirements may want you to have two different principles on line protection, where you can have a line current differential over one channel and a line distance over another channel. So there's definitely a place for that. Which is the percentage of use between distance protection and differential protection? Wow, that's a good question. I would say the predominant number of relays used in this country to date have been distance relays, but as I said, and most of those distance relays were used over things like power line carrier that really doesn't lend itself to, a dedicated power line carrier doesn't really lend itself to use for a line current differential relays because the bandwidth isn't great enough. But with the advent of more people using fibers now and depending less on power line carrier, you'll see that line current differential relay use will increase manyfold because of the availability of the communications channel. Okay, what else came up? Yeah, Elmo says probably 85, right? Current is probably 85. What is that? I don't know what the question was. It's probably, right now, it raises about 85% line distance versus 15% current differential now, but that is the amount of current differential keeps going up now. Any other questions we may have? Let's see, a question came up here. What is that? A question came up here. No. A question came up, how do you measure normal steady state current? I think this is when I was talking to the line charging computations that use in modern line current differential relays. Oh, and that is if you're operating at a level that's below the pickup of the relay, and if you're operating after the breaker's been closed for a period of over 500 milliseconds, it's considered to be a steady state condition, and that's where you measure the line charging current. Of course, every time the voltage on a line changes, either up or down, the line charging current changes. So that's why you can't do it consistently. You have to do it just every 500 milliseconds, every 1 second, to make that measurement. Okay, any other questions here? Do you have any document that you can share to us about the use of differential protection as a principal protection? There's many papers written about that, but I don't know of any. There's no documentation that says you have to use this, or that I know lots of papers being written about how it's used for protection. Can we use permissive schemes with line differential blocking scheme or permissive overreach? No. Permissive schemes and blocking schemes, permissive overreaching schemes are basically different ways of the communication logic works on a line distance relay, where you have line distance relays that are set to overreach the far terminal or underreach the far terminal, and sudden blocking or permissive scheme between the two of them. All of that kind of logic isn't needed for a current differential scheme, which just basically compares currents and then trips based on that. So you don't need those types of schemes that you have to make. You don't have to make it that complicated when you're using a line current differential. All of those schemes are used so that you can get 100% line coverage on a line distance relay, because you normally don't set the zone 1 relay to pass 80%. So that last 20% you have to cover somehow, and that's what the communications for the permissive overreaching schemes and the permissive underreaching scheme is used for. You're already covering 100% of the line section with the line current differential, so you don't need to have any auxiliary logic in the relay to do that kind of stuff. Okay, Aaron, any other questions come up? Yeah, Elmo Price will give a presentation in October on line distance relays, and he'll cover all these different communication schemes with you, and you'll be able to see the differences between the line current differential and the line distance, and how those schemes are incorporated. Next question. Would it be possible to explain how the angle is defined in differential protection relays? I barely know what angle you're talking about. How the angle is defined. What are the current limitations of the use of differential protection as a principal protection? The only limitation on a current differential relay is the channel. As long as you have a secure communications channel, you can use a current differential relay for that application. There's no limitations as far as having series compensated lines, having parallel lines, or any other a lot of limitations that are very short lines or very long lines. There's limitations on how you use a distance relay, like line, as there's just because of voltage drops and stuff, and there's limitations on using distance relays with series compensated lines because of the possible voltage inversions and that kind of a thing. But there are no such limitations when you use a current differential relay for those kind of applications. What is the best setting for the pickup current? The typical setting for a pickup current on a line current differential relay is, as I said before, about anywhere between 30 and 40% of the base current if you set the relay in primary amps. That takes into account any possible CT problems that you would have or anything else. Actually, because we use the line current with the line charge and compensation factor in it, you can actually reduce that down to like 30% or so for the setting of the minimum operate current. Now there are also other things in modern relays that account for CT saturation that you don't have to worry about, that you'd have to worry about in earlier vintages, about open circuit CTs, that you don't have to disable the whole system when you have an open circuit CT now. You can just raise the operate level to compensate for that. So there's those things that we have going for us in line current differential relays. If a communication channel is lost, the differential relays become overcurrents. Typically you have your choice. You could set up the line current differential relay so that it comes with a three zone step distance relay, and you can use that for the backup. But you have to provide current potential transformers for that to work. But you can use that for a backup. You can actually have that running in parallel with the line current differential if you wanted to. The old method of backup was to have, upon loss of channel, like in the old CB2 relay, you could revert to the relay to become a non-directional overcurrent relay upon loss of channel. And most people nowadays would rather, because you already have redundant schemes on the line already, will just disable this or use this as another impedance relay rather than use it as an overcurrent, non-directional overcurrent relay, because the possibility of misoperations for, not misoperations, but you lose any kind of directionality that way. When you say base current, is that the same as load current? Yeah. For example, if I have a 1200 to 5 current transformer, as the current transformer is feeding into this relay, then we would say that you could set the whatever current level you wanted to, but you could set the base at 1200 amps for the which would be the normal low current on the scheme system, and then in that case that would be the I base, and then the pickup level on the relay would be like 30% of that. You don't have to use that as I base, though. You can, if you have a 1205 current transformer, you could choose the base current to be as low as 600 amps, and then use 30% of that for the pickup level instead of. So it's actually up to you about what you choose for the base current. But most normally people would use the CT, primary CT value for what the base current is. What is the bigger distance kilometers that we can use line current differential protection? As I said earlier, that you can go up to, without repeaters, you could go up to 160 kilometers with the kind of light source that we have in our current relay for the LDCM module for the long range. 160 kilometers. If you put repeaters in the line, which means you would go into the center point and redo the light so that it extends further, then you could go further. But when you put a repeater in the circuit, of course, you're going to introduce some delay and more delays in the network. But 160 kilometers would be as much as we could for a single mode fiber. Okay, that kind of wraps up our presentation. As I said before, Tracy will send you all a link so you can get a copies of this presentation and the copy of the verbiage that goes with it. Thank you all for tuning in. Stay tuned. Well, our next webinar will be held in another couple of weeks, and you can look on your schedule for when this one's going to be. Again, the almost presentation on 9-distance relays will be sometime in October. Stay tuned for that also. It's been nice talking to you. Thanks for all sharing the line with us, and we'll talk to you again. And have a great day. Goodbye.